Dr. Cannara came to our original Google conference. It was our second conference. And if I remember right, he came as a pretty good skeptic, came to slap us around. I would encourage you to go to your local environmental groups and your local chambers of commerce, whatever you can, whether you call it advocacy or preaching or whatever, you should go ahead and do that. Here is Dr. Cannara, one of our great advocates.
Okay, so what I'm talking about now today, acidification of the oceans. And this is not a problem that was a surprise. It was actually discussed in 1896 and 1905 by Svante Arrhenius, who is the father of modern industrial chemistry. The chemistry that's affecting the organisms in the oceans that provide the basis for the food chain for 20% of all the human food protein on Earth. 20%. You imagine what happens if you remove 20% of the food protein available to all 7 billion humans on Earth, if you remove that within the next 10 or 20 years. This is called the carbon cycle. When you look at what happens on land with plants, basically the carbon cycle is neutral. Much carbon dioxide is emitted by plant respiration and bacterial digestion of plant materials in the soil, as is sucked in by the plants to make their cellular materials and so forth. So that's essentially a balanced system. The unbalanced now with humans for the last 150, 200 years has been our combustion fuels, which produce huge amounts of CO2, unnaturally so. And the isotopic makeup of this carbon is clearly fossil. In other words, if you do carbon dating on your Louis XIV chair, you will find out what the ratio of carbon-14 to carbon-12 is in its wood, and you can then establish whether or not it really is a Louis XIV chair or not. Well, by the same token, we know exactly where every carbon dioxide molecule in the air or ocean it came from. Did it come from fossil fuel burning or not? Here's the completion of the carbon cycle. Carbon cycle is completed in the sense of sequestration, which is a popular term. And sequestration is to limestone on the seafloor, and the limestone eventually can get subducted under tectonic plates as they move relative to one another. So that's where the carbon dioxide actually ends up, in carbonate rock, limestone, under the ocean. It can be recirculated into the hot molten part of the Earth, but it also can reside way underground for many, many millions of years. So this is the only true sequestration we have. Our problem lies in the fact that we emit 9 gigatons of carbon, 3 times that as carbon dioxide per year today. And we've been doing that for quite a few years. The carbon cycle that sequesters to limestone at the bottom of the seafloor only can sequester about 300 million tons. That's 30 times less than we emit today per year. And this was updated recently by a recent study in 2013. Went from what was originally thought to be about 200 million tons to less than 300 million tons. So it hasn't changed very much. The fact remains that what we emit is 30 times what the Earth can sequester. That is obviously the opposite of the word sustainable, right? So therein lies our problem. Our history is that we've emitted over 500 billion tons of fossil carbon in the last 150, 200 years. That's the industrial age. Obviously, in 150, 200 years, we're not going to be able to recycle that or sequester it. It takes 1,500 years to take what we've already put into the atmosphere and oceans for the natural carbon cycle to sequester back to deep storage. So therein lies our problem. We are 1,500 years behind the natural carbon sequestration cycle.
As far as like where coal and oil come from, does that sequester a significant amount of carbon, like subduction of rotting organic matter?
Yeah, I mean, coal and oil is underground and sequestered until we take it out, right? So that's good. That's clean coal. Definition of clean coal is what we don't use. If it's a gas, if it's converted to carbon dioxide gas, then this is the way it gets out of the system and back into geologic long-term storage.
Is the carbon being stored in limestone dependent on the animals not being able to make shells?
Yes, exactly. So is the carbon being stored in limestone dependent on animals being able to make shells and skeletons? Yes, exactly. So the reason this exists is because of life forms in the ocean. So the life forms in the ocean, like those little diatoms and so forth I showed before, that take carbonate ions out of the water, build their shells and their skeletons with them. When they die, they sink to the seafloor. Bacteria digest their hydrocarbon parts, but the carbonate parts become part of the limestone over centuries, right? So that's the cycle. So it's a life-driven cycle, sea life-driven cycle. And without that, there's no sequestration. There's not even the 300 million tons are not sequestered every year if those animals don't live. And the problem we have is that our emissions have, in fact, put them in danger. Here's an example. Off the Pacific coast at the top are many very small snails, sea snails, that are now showing evidence that they can't really form their shells properly or maintain them. And they are the basis of a sea food chain. Here, these are oysters from Alaska that can no longer mature because the water in the ocean is too low in pH. It's approaching acidity. It's less alkaline than it has been at any time in 300 million years. 300 million years. Now, 250 million years ago was the Permian Triassic extinction, which got rid of 90% of all species on Earth. In 150 years, we have brought the chemistry of oceans to a point not seen in 300 million years. All right, so here's another example. This is in the North Atlantic. These are sea urchin larvae. They're supposed to look like this. They look like that. These are other larvae, look like that. Norwegians are very concerned, other Scandinavian countries are very concerned because the North Atlantic is the most nearly acidic part of the oceans on Earth right now. In the upper right, you can see the dark reddish area showing the North Atlantic having the most carbon dioxide molecules per microliter. Here we are today in the blue vertical line. This is about 2050. The blue curve and the red curve indicate survivability of the species that do the sequestration to seafloor limestone. If those curves cross, it's all over. Before those curves cross, extinctions begin. And extinction is forever. It's not like global warming or sea rise, which might go back down. Once these animals in the oceans are extinct, they're extinct. It's like, you know, going to Vegas and betting your IRA on craps. On a few numbers, and the same number a few times in a row, your IRA is going to be extinct. Well, this is what's going to happen before 2050 if we don't get on the stick. There's a place called oceanacidification.net which summarizes a lot of the data from around the world that you can always go to. The top graph shows 25 million years or so and what we've achieved in just a few hundred years, a couple hundred years, right? We don't have very much more to go because if we get below pH 7.8 or so, we can kiss off most of the sea life that sequesters carbon dioxide. There'll still be jellyfish and things like that, but we better develop a taste for jellyfish, right? So this is what we've done. So this is pre-industrial, 8.2 pH, and we've brought it down to 8.1 on the average in just 150, 200 years. That's the entire average ocean pH on a planet. Pretty impressive achievement for one species on a planet to achieve in only 150 years to correct things. we're going to take the natural cycle that does the carbonate sequestration to the seafloor but via life forms, and we're going to reverse it. So what happens is the carbonate is sequestered under the seafloor. It gets pulled down under in an ocean trench between two tectonic plates, and some of it gets heated back into magma. The CO2 is stripped from the carbonate, and it comes out a volcano. Okay, so that's the natural cycle of things. What we need to do is do what we do when we make cement, but do it better. So when you make cement, you take 750 grams of limestone that these animals made at the base of the sea, and you heat it. You get the CO2 out of it, and you get the lime, and you have this lime now, which is calcium oxide, magnesium oxide, which is exactly what those animals in the sea really can use, and you take it back to the ocean and dump it in. So like we carry the mail, and we require aircraft companies to carry the mail, right? We can require shipping companies to carry the lime and disperse it in the ocean if they're ever going to use any of our ports. I mean, you can think of ways to do it. But the point is that we do what we currently do with the cement cycle, but we keep the carbon dioxide out of the air. Right. We have to keep the carbon dioxide from going anywhere into the air. If we look at how a real cement factory works, 10,000 tons a day of limestone go in, 5,000 tons of lime comes out about, and the CO2 going out through the furnace here is the rest. Right. So we need to capture that CO2, and we need to do something with it permanent. So these are other processes that have been suggested. Here's the sequestration of that CO2. This is a traditional idea. We pump it into an old oil well, but it can leak out through the clay and so forth. This is a new idea just recently published where you can take basalt, which is underground and all around the world. There's huge, vast amounts of basalt from lava. Remember, the lava that's spewed by a volcano has had its carbonate broken apart. The carbon dioxide has come out, and what's left is lime. So basalt has lime. Calcium oxide, magnesium oxide, iron oxide, other oxides in it. So you can actually take carbon dioxide, bubble it down through a water column that you're pumping, and just sequester it in basalt deposits that are loose. And that makes carbonate, rock, permanent storage. That can be permanent. So here's what we need to do. We need to dissociate limestone, take CO2 out, sequester the unusable CO2, perhaps use the carbon and split water, carbon and hydrogen, and make various chemicals, Kim and I, and there's another chemist that have talked about how to actually do that. But we can make carbon neutral fuels this way by simply taking the CO2 out of limestone, taking the resulting lime, put it back in the oceans, and proceed from there. This is a large amount of energy. And we need that energy to make the hydrocarbon compounds that we want to replace current fuels with. And then we're going to have a huge amount of CO2 left over from the reverse cement making process, right? Which we have to sequester. Remediation requires breaking apart limestone, taking the CO2, dealing with it, using it, sequestering it, taking the lime, dumping it in the oceans. And these are some of the numbers. These are kind of worst case because I'm sure the chemists and people who know catalysts and so forth can get to better ones. But the activity required here, requiring energy to do this, amounts to 91 gigawatt non-emitting power plants running 24/7 today. If we want to correct 30 gigatons of carbon dioxide emissions per year, then we need 10 times that. So we need a terawatt of power, clean power, no emissions, a terawatt of power just to do the CO2 work, breaking apart limestone, and sequestering the CO2 in some ways, using the CO2 for fuels and so forth. And then we have to have additional power to get if we want to get the H's out of H2O in order to make the carbon neutral fuels. So we're talking about several terawatts of non-emitting power that we need well before 2050, well before 2050, probably before 2035. You need to talk to your environmental groups, your representatives in Congress, our wonderful Congress, that we have a true Apollo 13 moment that we have to address very quickly, very substantially, even more substantially than simply replacing the existing fossil fuel power with clean nuclear, et cetera.
Just a question about the loss of sea life over here. That affects the loss of life of other land creatures too, I presume.
Well, whoever eats sea life that is bony or shelly, all right. Whether it's humans or other creatures like penguins and iguana, marine iguana, that kind of thing, will be affected by the loss of that food. Yeah.
I have heard it said with some of the climate-denying websites that other planets in the solar system are also undergoing climate change because of the increased radiation from the sun. Could you comment, please?
The solar cycle was diminished. The sun hasn't had as many sunspots. The Earth's orbit has differences in the distance between the Earth and the sun. Without carbon dioxide, we should have had reduced temperatures worldwide in the last 10 years or so, and we haven't.
Thank you, Dr. Cannara. Thank you very much.